The gas in this problem is taken from point A through B to point C. And in part A, we're asked to find the temperature at each of those locations. We'll do this using the ideal gas law. Solving it for the temperature, we see it equals PV over NR. We know all of those values, so we can substitute them. At A, the pressure is 2 times 10 to the 5th pascals. The volume is 0.01 cubic meters. There's 0.450 moles of gas, and the gas constant is 8.315 joules per mole Kelvin. That gives us a temperature there of 535 Kelvin. We can repeat the calculation, substituting the values at state B. To find the temperature there is 9350 Kelvin. At point C, we can either repeat the calculation again or realize that because B to C is a constant volume process, the ratio of the temperatures will equal the ratio of the volumes, and that gives us Tc equals 8/5 temperature at B. That works out to 1.5 times 10 to the 4th Kelvin. Let me record these values up here and erase this so we have room to solve parts B and C. Part B asks for the work done on the gas going from A to C. The magnitude of that work is the area under the curve on the PV diagram, and we can break it into two parts. The area of this rectangle with a base delta V plus the area of this triangle. So the magnitude of work is area of rectangle plus area of triangle. Base times height for the rectangle plus half the base times the height of the rectangle. And now we can substitute all the values. The change in volume is 0.060 cubic meters. The pressure at A is 2 times 10 to the 5th pascals, and the height of the triangle is 3 times 10 to the 5th pascals. That gives us a work of magnitude 2.1 times 10 to the 4th joules. The gas expands during this process, which means that the work done on the gas is negative. Part C asks us for the energy added by heat during this process. We can find that from the first law of thermodynamics. The change in internal energy is Q plus the work done on the gas, or Q minus the work done by the gas. Solve this for Q. It equals the change in internal energy minus the work done on the gas, and substitute values, canceling the two negative signs, to get an answer of 3.6 times 10 to the 4th joules.